Now we turn from why did we go to the moon and why did we stop going to the moon to the question of what did we find out when we went to the moon? And to address that topic, we've got, I'm very happy to introduce my colleague from NASA headquarters, Dr. Jim Green. He's currently our NASA Chief Scientist, the role he assumed in 2018, but before that he was head of the Planetary Science Division. And if you've been paying attention at all to what we've been doing with robotic probes around the solar system, you know that Jim was a very busy guy leading Lunar Reconnaissance Orbiter, New Horizons, Juno, Curiosity, the list goes on and on. Jim's a highly energetic and entertaining speaker, and I know he's going to tell us a lot about what we learned from him.
Thank you very much, Bill. It's a really great pleasure to be able to come and talk about some of the scientific results. And there are so many that I'm only going to be able to just touch on a few of those things. But of course, as we all remember, this is the 50th anniversary of Apollo 11's landing. Our three astronauts going off on a Saturn V, landing on the moon, and of course began science immediately. As Neil started to walk down the step, he looked out and looked down at one of the stanchions that are sitting on the moon and immediately stated how deep it actually had impacted in the regolith. And the reason he was doing that is there was quite a bit of controversy at the time. Many planetary scientists believed that there would be so much regolith. And regolith is ground up rock material that impact after impact builds up over time. There'd be so much of that you could easily sink down and not be able to return from it. And so that was the very first science that he did when he walked out. But soon after, when Buzz came out, they began to put out an array of instruments. Here is Buzz putting out a sounder. And this is a seismic instrument that will sit on the moon and be able to record any seismic activity. These would be potentially internal lunar quakes. Quakes that are caused by the Earth-Moon interaction tidal forces. That's one way they could be caused. Another way they could be caused is that the moon would be still cooling down. Even after 4 billion plus years, our planets are still in the process of cooling. It's like you bake a cake and you take it out of the oven and it's still cooking in, but it is indeed cooling off. And so that cooling off means it's readjusting itself and internal quakes could happen. And then, of course, there are impacts. Many planetary scientists, much prior to the Apollo program, felt that the surface where we're seeing these cratered regions were top of volcanic domes. And, of course, that turns out not to be the case at all. In the background is another really exciting instrument. It is a retroreflector. This is, I believe, Buzz, you also put this out, or Neil put that out? Okay, Neil put that out. Thank you. I didn't know that. And so Neil put that out, pointed into the Earth. It's a passive instrument, and it's really all about sending a laser beam from the Earth to the moon, reflecting off this set of 1.5 foot by 1.5 foot mirrors, and having that beam come back and then timing it. All right, and we've done that every year for the last 50 years. So why do we keep repeating that measurement? Didn't we get it right the first time? You know, the speed of light hasn't changed. And so that's an element of the science that was done by these exciting missions. From here on, we have, as John talked about, 11, 12, of course 14, 15, 16, 17. These are the locations that they landed, all on the near side. Near the equator and in mid-latitudes, not to the poles, not to the far side, all right? But indeed, in very important regions. Some of these regions are in these dark regions called Mare. The concept that when you look at the moon years ago, they look like seas, so Mare is the name of a sea. In reality, what they are lava flows. and they flow into huge impact regions. And so these are huge impact basins. And of course, we know that from the material that we indeed brought back. So out of all the litany of things, I have just selected a few things to point out as what I feel are some of the absolute top discoveries. The material we brought back, and there was about 850 pounds of lunar material. So that's rocks, that's regoliths, and it's cores, where we've gone down a meter or more. And these soils then are in tubes, and in fact, they have laid pristine in our archive. We're going to be opening one of them in the December timeframe. And then this one we're really excited about. It's an Apollo 17 tube, for which we're going to also look at the volatiles that may also be trapped in this tube that may come out. But the rock information was so valuable that we began immediately to learn a number of important things that you could not do in any other way. The first thing is the moon is old, 4.6 billion years old. The oldest rocks you can find here on Earth, they're the Australian chert, and there's a region up in Greenland, for example, are about 3.8 billion years. All right, so as geologists walking around the Earth finding these old rocks, that they might be tempted to say that that's how old the Earth and perhaps the moon is. And these rocks clearly demonstrated that the Earth-Moon system was much older than that. Okay, and the reason, of course, is because our planet is very active geologically. We have plate tectonics, we have atmosphere that creates erosion, wind erosion, weathering events, and oceans, of course, and that changes the geology of the surface. In fact, we now know for every one crater on the moon, 20 similar size has hit the Earth, all right? And yet the Earth is not pockmarked like the moon. And that indeed is one of the more important things that we found out was the impact processes are really the dominant geological processes on the surface of the moon. We also found from the laser ranging system that the Earth and the moon are separating. The moon is moving away from the Earth about 1.5 inches a year. This is one of the reasons why we keep doing this experiment. We indeed want to measure that and understand what's happening there. And of course, the interaction, the tidal interactions, and the dissipation of that energy in our own oceans is causing the retreat of the moon. But any origin theory of the moon would have to take into the fact that the moon has been making that motion for billions of years, and so the moon must have been created very close to the Earth. Now, the other material that was found when we brought back these rocks and looked at them isotopically, you know, that we have the same isotope ratios between the Earth and the moon rocks. This was really a telling tale that the Earth and the moon had a very similar origin. And the concepts of previous theories in terms of, well, this body was moving by and we captured it, are just not going to work. That was almost an impossible one anyway to think of. In fact, what we also brought back was anorthosite. Anorthosite is a very important rock. It actually can float on top of lava. And we brought it back from Apollo 11 on, and this clearly indicated that at the origin of the moon was a massive molten rock material on that surface, for which then the anorthosite was able to float to the top for us to then be able to bring that back. So these theories these pieces of information were being put together and actually helped support one of the theories, which is what's called the giant impact hypothesis. So let me take you back about 4.6 billion years, and the concept is the proto-Earth is coming together, it's acquiring material, it's clearing out its orbit, and as it does so, other objects near us are doing the same, and they are beginning to accrete also. And an object we call Theia, approximately the size of Mars, slams into the proto-Earth. That material comes together. Theia is totally ripped apart. Material out to a certain level that cannot build another object. We call that the Roche limit. It's sort of like the rings of Saturn are all inside the Roche limit. It's very hard to accrete and build larger objects in that limit because gravitational forces tear it apart. That material, which is then falls on the Earth, but away from the Roche limit, a new object begins to accrete. A new object begins to form, and that object ends up being indeed the Moon. And so conceptually, the Earth and the Moon are very close together. It's believed that the Moon, which was formed at the end of this giant impact hypothesis, is only about 3 Earth radii away. And indeed, the Earth, therefore, has to be spinning much faster. As a ballerina spins and then pulls her arms out, conservation of angular momentum says she slows down. So to get a 24-hour day with the Moon that close, and to be consistent with the observations that we talked about, means that the Earth was spinning once in 5 days. Now this allows us to sort of think about sizes. In terms of as we see the Moon today and as we think about how large the Moon might be in the sky, it's 16 times larger when it reformed at 3 Earth radii. Right now the Moon is 60 Earth radii away from the Earth. And so consequently, the Moon, if you were on the Earth at that time, which I would not have recommended, and you'd have to watch it pretty fast with a 5-hour day, would be dominating the sky. It would be absolutely enormous, 16 times than the current Moon that we see today. So these are really spectacular observations. The Moon, as we see it today, of course, we can make these measurements from Lunar Reconnaissance Orbiter, and we see the far side is so much different than the near side. In fact, we're able to determine that on the near side, these giant impacts actually brought up a lot of molten material in the crust and deeper from the mantle, flowing onto the Moon, creating these mare. And those are younger than the initial lunar magma ocean, this lunar magma crust, which formed at the beginning of its formation 4.6 billion years ago. And so that means we can use the impacts, their density, and knowing the rock ages to create a chronometer in terms of ages. Now, how old certain regions are on the Moon depends on crater size and crater density. And as you can see, we've been using that from just the samples we returned from Apollo to sort of age date many different objects throughout the solar system. So the Apollo material that was brought back was really critical in allowing us to use that information to understand formation processes going on throughout the solar system. Another really spectacular set of observations that we make today, this is an altitude where we see the highs are the reds and the whites, and the lows are the blue or the purples. And we see on the far side, huge variations in height, about 14 or 15 kilometers. Well, here on Earth, to get even 11 kilometers in height variation, you got to go to the top of Mount Everest and the bottom of the Marianas Trench. So huge variations in height are occurring on the Moon. In fact, this far side, this low area on the far side, is actually another impact region. You can actually see it. It's an old region because you can see many other impacts are on top of that. And that particular region right here is called the South Pole Aegean Basin. So we have the basins here are full of magma. We have huge impacts here that aren't full of magma. And so there is indeed another effect, we believe, of tidal forces, perhaps even crustal thickness, that's allowing the magma to flow into impacts huge basins on the near side, but not on the far side. So we've then been able to, because we know the dates of the rocks, and we can use the chronometer to begin to match these large basins, both on the near side and the far side, and determine their ages, okay? And what we're finding, which is really quite exciting, is that many of these basins, and many of these large basins, are actually relatively young. They're not as old as 4.6 or 5 or 4.4 billion years. These are between 4 and 3.8 billion years ago. Now, we've known this for 40 years, okay, once this was teased out. And I have to say, the planetary scientists really were struggling to understand how this impact of these large basins occurred so much longer, 600 or 700 million years after the basic formation of the moon. In fact, we called that in a very special way the late heavy bombardment. Well, recent computer modeling in the last 10 years or so has really given us the explanation for it. And it has to do, it has to do with how we form the rest of the solar system. In the early 2000s, a number of the computer codes that were actually being developed that would model putting together entire solar systems were coming to fruition. In a meeting in Nice, many of these scientists came, Nice, France, many of these scientists came to talk about what their codes were doing and how they could create the solar system. And to the person, they could not create the planets, even running their codes, 4.6 billion years in the positions they currently are today. And so that night they went out drinking, and of course you're in beautiful Nice, France. And so as the wine flowed, they began to talk about, well, what your codes have and what they don't have, and would that make a difference if you add these changes and take these cores that you put out there and then accrete the planets faster? All the kinds of mechanisms they're talking about. Finally, one of them said, well, look, let's just figure out how to make 9 planets, and the big ones in particular. Because we couldn't form Neptune and Uranus and Neptune, or even mostly Saturn, after running our codes 4.6 billion years. Maybe we can figure out a way to do it. And another one said, the only way I know how to do it is we put them closer to the sun. And so they ran those codes with planets closer to the suns, and they made them in 10 million years. But running the codes much longer than that, gravitational interaction between Jupiter and the large, giant planets, Saturn, Uranus, and Neptune, caused a huge push. And that push is a gravitational resonance. Jupiter moves inward, Saturn, Uranus, and Neptune moves outward, and in that, it changes the distribution of the small bodies everywhere. At almost the right time as this late heavy bombardment, bombarding everything inward into the solar system. And that fit perfectly well with the observations that we have brought back from Apollo by dating those rocks and understanding the dates of the basins that they represent. And so today we have a solar system that looks like this. A lot of credence comes now from looking at this very process on exoplanets. We find huge Jupiters in orbits close to the sun where they couldn't possibly have formed. They needed to be moved there. And so gravitational interactions between giant planets are throwing one out and one inward and changing the dimensions of those solar systems and moving the planets into new orbits. We're seeing that in many, many examples now in exoplanets, and that gives even more credence to the Nice model. And so today we have some exciting things to do when we go forward to the moon. And that is, we need more samples to be able to do a better job of getting our chronometer right. We want to be able to understand more of the details of the giant planet migration. Of course, we have found enormous amounts of water in permanently shadowed regions in the north and the south poles, which is one of the key resources that is focusing our attention to have our program land there and use those resources. But there's many other elements that we want to know about. So for instance, the history of our sun via the solar wind is buried in the far side of the moon. You know, when you see the moon and the moon is full, it's in our magnetotail and protected. But when the moon is new moon, that means the sun is lit the far side, and that is in the solar wind, and that's what is being implanted is that solar wind history. Even though we put seismic instruments down on the moon, we had a very difficult time analyzing the data because they're crossed rings. And actual moonquakes are very difficult to pull out. We now understand that process and can build much better magnetometers that would give us, seismic systems that would give us a better idea as to the size of the crust, the mantle, and the core, which is what we really want to understand and would verify this giant impact hypothesis. And of course, the far side opens up new wavelengths of study. So this is an exciting time for us. The future of the moon, based on the next series of things that we want to do, is based on the science that comes from Apollo and the orbiting missions that we've done in the last 10 or 15 years that really extend our knowledge of the moon and allow us to think about further science and exploration that we want to do. How we're going to learn to live and work on a planet utilizing the resources that are there. And in fact, it's not only the water in the South Pole Aitken Basin. The magnetic field anomalies clearly indicate that there are resources of platinum group metals and irons and nickel and many other types of things that are in that area that we are depleting, for instance, the platinum group metals in particular, here on Earth, and would need and seek other regions. And this is where mining and manufacturing might come to our future. So indeed, in these few minutes, I hope I've given you at least a little idea as to the exciting science that we want to do going back to the moon. And once again, it's all largely based on what the Apollo missions have done for us. Thank you very much.
Thank you, Dr. Green. That was great.